Okay. Oh, nice. So I can see it. Okay, perfect. So let's get started, I'd say. Good morning. Good morning, everyone, and welcome to our next OpenCloudification webinar. Today, I'm here with Michael, that he's gonna provide an interesting talk about multi-party computation and confidential computing. This is a topic that we continued already on several webinars because we saw that there's an interest and there were requests from the audience to know more about, and there's a lot to talk about. That's why I would like to thank Michael for being here already and giving this surely interesting presentation about it. Let me give a short introduction on OpenCloudification in general as our project, if you never heard about it. So OpenCloudification is one of the projects organized and managed by ELSEC. We are a cybersecurity company, no-profit organization. We really try to innovate in the field of cybersecurity, and to do that, we span and we cover a broad range of different topics, including cloud technologies and open cloud technologies, as you could guess by the name of the project. And we're doing this project thanks to Vlaio. We've been funded to help other companies getting into or taking the next step on cloud technologies, with a focus on open source technologies specifically. We have a website, opencloudification.com. There you can see all the activities that we organize, from the past recordings of all our webinars to all the documentations, white papers, anything that could help you get started. This project is a collaboration of ELSEC, as I said already, IMEC ID Lab, and the Beacon. So what we try to do is have tangible results. So we're not just explaining how things work, but we really want people to take the next step and start using open source technologies for the cloud. We do that presenting and disseminating information about open source technologies, like we're doing right now with this webinar, but we're also present in a lot of activities and events in which you can come and talk to us, so we can find a way to help you more practically. Because open source technologies are a broad topic. A good example is the Cloud Native Foundation. In this case specifically, as you can see, the landscape of all the available technologies is quite big, meaning that if you don't know where to start or how to proceed, then you might probably need some guidance and some help. And this is the reason why we're here, and we're trying to talk about something that could be useful to fully understand a specific topic. In this case, as I said, today we're going to talk about data processing of IoT with multi-party computation. So I would like to invite Michael to join me here on the stage. And with that, Michael, again, thanks for being here, and the floor is yours.
Yes, thank you, Luca. Let me first try to share my screen. I think you should now see my screen.
Perfect.
Okay. So good morning, everyone. Thank you for joining this webinar. I will be talking about MOZAIK. MOZAIK was a research project we have completed over the past 4 years together with a couple of universities here in Belgium. And in MOZAIK, we explored different ways to do secure and privacy-preserving computation on data. And we've mostly focused on IoT data. But the concepts I will be describing today can be more generalized to other data as well. So I will be presenting a proof of concept, and the design that we have built is built around the proof of concept. But that does not necessarily mean that the concepts I will be describing today are only useful for that proof of concept. You can also generalize this for more other use cases. I will be presenting a rather high-level overview because of the technical details are quite difficult to explain sometimes. So I will be linking some useful documents along the presentation with useful deliverables, papers that might be of interest if you want more low-level details. But first, let me start with a quick scenario about why we have initially explored this research area. And for example, a lot of people are wearing a smartwatch today or other health sensors, and those devices constantly collect health data. For example, the heart rate of a person, their blood oxygen level, and most of these smartwatches are proprietary, and they have proprietary software from big companies. And depending on the brand of smartwatch, the data is also collected and stored on servers in the cloud. Let's say, for example, Google, Whoop, Apple, and Garmin are leaders in this space. I might have forgotten some other important ones, but yeah, they store your data, and it's really convenient for the user to have your data stored in the cloud. And then this data can also be processed with some sort of AI to then get some anomaly detection. This is very useful for the users, of course, but the problem with this approach is that the user does not really have control over its own data. They don't really know where the data is stored or who owns the servers. They don't know who is processing their data, if it's the companies themselves or if they outsource it by a third-party provider to do the anomaly detection. So not everyone is keen that their personal data is stored in the cloud and processed by servers they do not own. And disabling certain features like this defeats the purpose of owning such a device. So what we want to have is that users can have such a device without having the privacy risks of storing their data in the cloud. So more generalized, the problem is that we have high amounts of data, and in this case, we call it IoT data, but this can also be generalized to all kinds of environments in healthcare, smart cities and homes, but also industrial systems, industrial IoT systems, cameras in cities, all types of data. And yeah, if we want to do something useful with that data, we need to store that data at least temporarily for some time. So we need a lot of storage. And if we want to process that data to get insights, for example, using machine learning, we also need some sort of processing power. And most of these devices that are located, that are deployed in the world, they don't really have enough processing power and storage to do that. So the solution is that a lot of these devices offload this to the cloud. And yeah, this is the problem I just described, because then all the data is in the cloud, mostly unencrypted, and this has some privacy risks. For example, what about sensitive data? What about regulation, GDPR, for example, in the European Union? And these are all problems that we wanted to tackle with MOZAIK. And for MOZAIK, we then created a proof of concept where we have an end-to-end solution where the data is encrypted at a source, and then also while it's processed, completely privacy preserving. So no information is leaked when the data is being processed. So we have some requirements in this system. So yeah, we need to securely collect the data. So make sure that the data, when it leaves the user's control, is encrypted and secure. We need to make sure that the system supports analytics and decision making, because yeah, if you have encrypted data, it's a lot harder to do any types of data insights. And the system should also be very scalable and performant to make sure that if the amount of IoT devices scales, that the system also scales with it. And an important factor here is that we build this architecture from the ground up with data protection and security in mind by default. So that means that while previous systems 10 years ago, 20 years ago were designed first and then security and privacy was an afterthought, now we really designed the system to make sure that it is secure by design. And also something that is also very important also for GDPR is that the user is in full control over their data, that they can revoke access, revoke consent at any time. A very quick overview of how our proposed solution looks like. And although this is very catered to one of our use cases, and the different concepts I will be explaining are applicable to different also applicable to different other implementations, different use cases. So in this case, we have an IT sensor that either encrypts their data on the IT sensor or on a gateway. I will describe the differences in just a moment. And then when the data leaves the user space, so the left side here is the user space, it's encrypted. So the data is fully encrypted when it leaves the user's control, and then it's stored encrypted. Let's now consider this big square in the middle as being a data store. And on the right side, we have the processing parties that will do the actual computation. And then lastly, we have a model provider that can provide machine learning models. So if third-party companies have certain machine learning models that they want to rent out, without fearing of intellectual property being lost, they can also do that here. This has been a collaboration between 3 major Belgian universities in Belgium, KU Leuven, University of Antwerp, and then Ghent University, where I am part of. And in KU Leuven, we have 2 different teams. We have the MOZAIK team, mainly focusing on the cryptography and security side of things, and then we have CITIP, who was mainly involved with regulation and compliance. And then the University of Antwerp was mainly working on networking, making sure that everything, that the data was being transmitted correctly, securely, and mostly using 5G network slices to make sure that the data throughput remained consistent. And then we, Ghent University, was mainly an integration partner. We did a lot of design choices, and then we implemented a lot of different components so that all the different components from the different partners work together neatly. But let me first introduce myself before I move on. So I'm Michiel van Kenno. I'm a PhD candidate and also teaching assistant at IDLab, which is a research group at Ghent University in collaboration with IMEC. And my PhD topic is actually very broad. It's secure edge, fog, and cloud. But I'm mainly working on WebAssembly at the moment on the embedded side, and also how we can utilize WebAssembly on the edge and the cloud. Before I move on to the different components of the system, I will quickly first give an overview of privacy-preserving computation, which was the right side of the diagram I just showed. Because this is important to understand the rest of the design choices we have made, because there are some limitations and things we have to consider to create a system that works together with these technologies. So what is privacy-preserving computation? Well, there are different privacy-enhancing technologies to allow or to enhance the privacy of the data that's being processed. So we have differential privacy, for example, or synthetic data generation. And the main goal is that we want to perform computation on the data without compromising the data privacy or the data owner's privacy. And in this, in MOZAIK, we then looked at 2 different computing on encrypted data techniques. So that means that we effectively do computation on data that has been encrypted before or is encrypted at the moment. And then we started out with MPC, which stands for Multiparty Computation. And in this case, the data, even though it was encrypted, will first be decrypted in a distributed way, in such a way that the different parties don't, even though it's an unencrypted share, it's only a share. So that means that with only one share, it still doesn't leak any information about the data. And then we also quickly explored fully morphed encryption, which is essentially doing encryption on encrypted data. So the data is never decrypted, but this has some overheads, which I will explain later. But multiparty computation, also known as secure multiparty computation, is a cryptographic technique where multiple independent parties will work together jointly to compute a certain public function without leaking their private inputs to any other party. So that means that they will work together, but they won't collude. Because if they collude, then the privacy is not guaranteed anymore if they collude above a certain threshold. For example, if you have 3 parties and 2 of them collude, then the privacy is, in most cases, not guaranteed anymore. But we also have some network overhead with MPC because the different parties need to communicate with each other. A very simple example to grasp MPC is to calculate the mean salary in an organization, which is a very common example. And let's, for example, say we have three parties, 3 employees of a company, A, B, and C, which have a salary of 70, 80, and 90 respectively. And we want to know the mean, which is 80 in this case. But the different employees don't want to share their actual salary. So how would we do this in MPC? Well, it's actually quite easy. So each party or each employee generates 3 random shares that add up to their salary. So for example, A has a salary of 70. If party A then generates 3 random numbers that add up to 70, we can then share 2 of those random numbers with B and C. So A is then, for example, 15 plus 35 plus 20. A keeps 15 and shares 35 with B and 20 with C. So this is what we call splitting it up in secret shares, so that every share is secret. So it means it is an original part of the data, but it doesn't tell anything about the actual data itself, because 35, for example, doesn't give any clue to the real salary of A. And every party does this and shares their secret shares, 2 of them with other parties. So A will share 35 with B and 20 with C. B will share, in this case, 40 with A and 30 with C. And C will share 50 with A and minus 20 with B. And these are just random numbers I've chosen. You could easily do this exercise with other numbers, and you will see that you will also have the same result. But so now everyone holds a share of everyone's salary, but they actually don't know the real amounts of the salaries of the different parties. Then every party can do a local computation. So A will do 15 plus 40 plus 50. So 15 is the one number A kept from the original secret share split. And then it takes 40 that it received from B, and it will add 50 that it will received from C, and it will come out to 105. Still doesn't really say anything about the other parties, their salary. And all the different parties do this, and then we have 3 different numbers. And now the 3 parties will then share the 3 numbers with each other, and each MPC party can then independently compute the average by adding the 3 numbers together and dividing them by 3. And then we see that we also have the end result of an average of 80. So in this case, in MPC, we successfully calculated the mean salary without revealing the actual salary of the 3 parties to any other party. Then we have the other sides of that we explored, and that's FHE, which is fully morphed encryption. And here we do actual computation on encrypted data. So the data is encrypted in such a way using different types of encryption keys, using different algorithms in such a way that we can process the data while it's encrypted. So we can gain useful insights from the data in fully encrypted form. But we've seen some downsides to it, that it has a very high computational and resource overhead. Then I'm talking about very powerful CPUs, a lot of memory usage. And then we've seen that the key material, so you have different types of keys, and different keys are needed for fully homomorphic encryption, can get quite large. And if you need to transmit them over network, you also have a lot of network overhead. This was some very high level and brief introduction to MPC and FHE. But if you are interested in getting more low-level details, I've put some links on the slides right here. The first one is a presentation given by the people from KU Leuven COSIC on MPC. The second link is about an introduction to distributed symmetric encryption, so how we can decrypt something in MPC without revealing anything about the original data. Also an introduction to FHE, also given by COSIC, and these are all very low-level technical presentations, which are very interesting if you're interested in any of these technologies. And then some two relevant deliverables that we have written, which are more catered towards the proof of concept we've built at MOZAIK, and how we used the MPC and FHE in MOZAIK. But now let's move on to the different components that MOZAIK has. And I will quickly go over each component and explain how we implemented them and why we implemented it that way. So let's start with the encryption at the source. So an IT sensor or the gateway will do the encryption. So the IT sensor is the actual sensor that will capture the data. This is, for example, a heart rate sensor, but it can also be an air quality sensor, a camera, whatever you want it to be. But in this use case, in this proof of concept use case, we have chosen the heartbeat data IoT sensor. And then the IoT sensor can either transmit the unencrypted data to the gateway, or it can already encrypt it on the IoT sensor and then transmit the encrypted data to the gateway. This all depends on how powerful the IoT sensor is, if the IoT sensor has access to the internet or not. Because, for example, if the IoT sensor is a Bluetooth device that does not have access to the internet, it will need to transmit the data to, for example, a smartphone, who will then do the actual encryption and sending the data to the cloud. So if we look at this in a more technical sequence diagram, we can see that the user will generate a key. Okay, this is a symmetric key, and it will store that key to the IoT device. For example, this is just a scenario where there's no gateway involved, so the IoT sensor has, in this case, we assume that the IoT sensor has enough computational power, and it has access to the internet. So so in a certain loop, the IoT sensor will measure some data value, which we call D, and it will then encrypt that data value D with that symmetric key. So then we have a ciphertext of the encrypted data, and this is what we then store in Obelisk. Obelisk is then the data store, which I will explore in just a bit. So this is a MOZAIK Obelisk, and like I just said, Obelisk is the data store we use to actually store the IoT data. But Obelisk itself is not privacy preserving in a way, so we built a lot of components around Obelisk to make sure it works together with MPC and FHE, so that we can enable the privacy preserving computation. Here we also applied some common techniques like authentication and good role-based access control, so that different users cannot access other users, their data, that the MPC parties can only access data they have been explicitly granted access for, and so on. And lastly, we have the MPC parties and the FHE server, which will do the actual computation. So the parties, if it's MPC or FHE, they will all receive an encrypted string or encrypted bytes of data. And in MPC case, yeah, you can only in MPC you can only perform computation on that data if it's unencrypted. So you first need to do some decryption, and in FHE it can automatically do the analysis on the encrypted data itself. So yeah, the user's data needs to be decrypted before the computation in MPC, because otherwise you cannot really gain valuable insights with, for example, machine learning. So they need a way to somehow decrypt it without revealing private data. So they will do some distributed decryption, and this will result in decrypted secret shares. So the secret shares I talked about with the mean salary example, those shares are unencrypted data bits, but they don't tell anything about the actual data itself. So after the distributed decryption has finished, so they will work together and decrypt the data, each party will have decrypted secret shares. So what's important to note here is that, yeah, if different MPC parties then collude, then we lose the security aspect because we have decrypted secret shares. So if you add the secret shares together, then you end up with the original decrypted data, which is something we don't want. So in this case, we assume that the MPC parties do not collude. But of course, yeah, decrypting something requires decryption key. But the problem here is that, yeah, we cannot store the decryption key in the system, because if we store the decryption key alongside the encrypted data and someone breaches the data store, all the data is still lost. So how we do this is we split the decryption key also in secret shares, so that every MPC party receives one secret share of the decryption key. Again, one secret share does not tell enough about the total decryption key, so one secret share is kind of useless. And because we can also, if we store all the different secret shares together in the data store, then we have the same issue, because then we still have, even though they are secret shared, if you add them together, you end up with the original decryption key. So what we do is we encrypt each secret share of the key, also with the public key of the MPC party that needs to receive that key. So we split the key. This is what the user does before the computation starts. It splits its secret key K in 3 shares, and it will then encrypt every share with the public key of the MPC party. So MPC party 1 will receive an encrypted with their public key. So with public key 1, it will be encrypted, so it will receive an encrypted version of K1. And then MPC party 2 will receive an encrypted version of K2, and MPC party 3 will receive an encrypted version of K3. In this way, we can store the different secret shares also locally in MOZAIK, because they are encrypted with the public keys of the MPC parties. And then afterwards, when the MPC parties will do the actual computation, they first need to decrypt their share of the key. So they will first use some basic asymmetric decryption algorithm to decrypt their share. So every party will receive then the share, a small share of the key. And then the actual computation happens, where they will first do the distributed decryption, where the input is the ciphertext of the data, and also an input is the key share. and then some other associated data, which I just omitted right now for simplicity. Then the actual inference happens. So this is machine learning inference. So we receive, after distributed decryption, we receive shares of the data, secret shares of the data. And then the MPC parties will work together to do the actual machine learning inference using those secret shares they received. And this results in secret shares of the machine learning inference result. So this is the result, but it's still secret shared. So one share still doesn't say anything about the actual result. And then we can reverse the process of distributed decryption by doing distributed encryption, where we take the secret shares of the inference result, the shares of the key. The different MPC parties will work together, and then we'll encrypt the data again, and then we end up with a ciphertext of the result of the machine learning inference result that's encrypted again with the secret key of the user. Now let's quickly take a look at how we implemented this IoT sensor in MOZAIK. For MOZAIK, we have a whole proof of concept implementation, and therefore we didn't use a real IoT sensor. We just implemented a simulator, and we used a very popular ECG dataset that's readily available. And what we just do is we just read samples from that data set, encrypt the data using a lightweight encryption algorithm, and then send that data off to the gateway or MOZAIK Obelisk directly. We have two operating modes, like I just said, on-device encryption or delegate encryption in the gateway, depending on how powerful the device is and if it has access to the internet. What is also something I want to mention is that everything that we have implemented in this project is open source, and I will have links to relevant components on the slides when necessary. So in this case, you can, if you go to the GitHub organization MOZAIK SBO, you will have a list of all the repositories that are open source. This is just an example of how this would look when we run the IoT sensor simulator, not really that important. Then the gateway, this is an aggregation point. So let's assume you have a smart home, and then we assume that the smart home is a safe environment, even though that's not always the case, but let's assume it is. Then we have maybe one gateway that all the IoT sensors connect to. And then the gateway will do all the encryption of the data, and it will also perform some caching if necessary. And for example, it can also be a smartphone. For example, if your smartwatch or sensor doesn't have internet access, so it can work, for example, with Bluetooth. This is also not that important. This is just an example of the gateway running. But now let's focus on Obelisk, because I've talked about Obelisk a lot, but I haven't really explained what it is. So Obelisk is mainly a cloud-native solution for time series data. But it's not just time series data, as you know. It's a lot more than time series data, because Obelisk supports a lot of different complex data types, for example, JSON objects and strings and arrays, whereas most of the other time series databases only use very simple primitive types. And Obelisk was actually first developed in 2016, or it started in 2016 for a project called City of Things. And that project wanted to investigate how multiple sensors all across a city can all be aggregated in one data store, so all different formats. And for that, they needed a very high-performant IoT platform that could ingest at a high frequency, so a lot of sensors, a lot of different formats. Later on, a lot of projects also wanted to query that data and also wanted streaming access. So then that was also implemented. And yeah, when Obelisk was first developed, there were some requirements, but the developers knew that, okay, we know that the requirements will only go up in the future. So they also made sure that Obelisk was very scalable to make it future-proof. Yeah, and since 2016, multiple iterations of Obelisk have been developed. Iterations on some of them focusing on ingest performance, others focusing on streaming performance. And now there is a new version being developed right now, which works with different plugins, so that someone can choose, depending on their use case, which components they need. And the latest version actually implements a lot of things, a lot of lessons learned from the previous almost 10 years now. Some use cases that Obelisk is useful for. Yeah, you can just use that as a general purpose time series database as an alternative to other popular solutions out there. But depending on your use case, Obelisk might be a better fit if you need, for example, more complex data types. Then yeah, the second use case is where it was originally developed for, smart city, industrial IoT systems. And the reason why this is such a good use case is that Obelisk has very good multi-tenancy support. So you can organize and isolate data with different roles and different permissions. You can delegate different permissions, you can inherit permissions, and so on. You also have very fine-grained access control. So you can restrict certain users to only certain time ranges or certain labels. So if you need some third party to access a little bit of data, but not all of them, you can really restrict what they have access to. And then there is also a geospatial component, so you can query data based on a certain region or location. And the third use case, which Obelisk might be useful for, is as a pure data sink. So you just stream all your data in Obelisk, and then later, when you want to do some machine learning processing, you can then query all the data. So this is very useful if you have a lot of high frequency ingestion of events that then later needs to be processed. Obelisk itself is a microservice-based architecture, which is very, or not very, but is rather complex with different services. And there are 3 services I want to spend a little bit of time on, and that is the ingest service, the sync service, and the streaming service. Because you can see that we have a message queue in there. And the reason for that is that if we have a lot of data coming in, we don't want the ingest service to be a bottleneck. So what we do is the ingest service, when it receives a data point, it just puts it on a message queue without really processing anything. So it will not do any data cleaning. It just puts it on a message queue, and then the ingest service can respond with a 204 to the IoT device. This way, we eliminate a lot of latency for the ingestion side. And then we have the sync service, which is then a consumer on the message queue who will, on their own pace, store that data in the data store, and it can do that in a batched way. For example, if a lot of data points come in, it can batch that data to the data store. So we have a better throughput. And then to limit latency, for the actual data storage, there is a limit of 2 seconds. If a batch hasn't been filled for 2 seconds, then the data is also stored. And then the streaming service is also another consumer of the message queue. So if someone wants to stream data that has certain labels, for example, then the streaming service listens to the message queue and then forwards the data that should be forwarded to the correct user. Then we have some other services like the query service, which is very obvious, just query data, and then some identity and access control services. When we map this to different technologies, the actual services are built using Quarkus, which is a Java Kotlin modern alternative to microservice application software. I forgot the name. It was Spring Boot. So it's a modern alternative to Spring Boot. For message queue, we use Kafka. And then the actual data store is using ClickHouse. And even though ClickHouse is just a regular column store, when designing the schema for Obelisk, it was designed in such a way that it works well with time series data. Then we have OpenFGA, which is for fine-grained authorization. So you can really apply fine-grained access control rules to different users. And then for authentication, we use Keycloak. And the reason why we use Keycloak for that is that the developers of Obelisk tried their own authentication system before. But when there is a security vulnerability, they have to spend time to fix it. And at a certain point, they were mostly fixing security vulnerabilities instead of really focusing on the actual implementation of Obelisk. And that's why they use Keycloak. It's an open source identity manager. And it's well maintained, and security vulnerabilities are patched very quickly. Everything in Obelisk uses just regular HTTP APIs. So ingesting is just a simple HTTP post, and querying is just a simple GET. And the reason why this is just because it's simple, and also because you can have really good documentation for that. Like I mentioned before, Obelisk is a cloud-native first system. So it really made sure to use a lot of cloud-native CNCF dependencies, for example, OpenFGA. And it also heavily uses Kubernetes, for example, ingress controllers, secrets, config maps. So different services can share some secrets and so on. And Obelisk is designed in such a way that it is in the different services can scale independently. And it's also a fail-fast approach. So instead of trying to handle or trying to fix certain errors that might occur in a service, sometimes it's faster to just crash the service and then let Kubernetes handle the crash, and then Kubernetes can just bring up a new instance of that service. We have some resources about Obelisk, because Obelisk is also open source. We have a version that is currently a live version. This is version 3, so this is before HFS. HFS is a high-frequency streaming version of Obelisk, but Obelisk version 3 is the one that's being used heavily at the moment. Then Obelisk Core is the one that will work with the plugins, like I mentioned, and information about it is available on the second link. And then it's also open source. We have the version 3 open source on GitHub. And then the Obelisk Core version, the current open source version, but it's still in development mode, is available on our GitLab. Let's dive deeper into the different components that we have alongside Obelisk to build the privacy-preserving computation data storage. And let's first start with the API, which is just an overarching API. And this is built in such a way that this is actually the only publicly available service that might have access to the data. But keep in mind, the data is still encrypted. And also the API is a little bit of a middleman between the user, the MPC parties, Obelisk, and other components in the system. And just as Obelisk, it's very well documented using OpenAPI. anyone could easily use this. So if a new MPC provider wanted to integrate their MPC parties with MOZAIK, they could easily do so. MOZAIK also uses Keycloak, just as Obelisk, and we have two different flows. The first one is only for Obelisk authentication, and the second one is needed for web authentication. The reason this is different is because MOZAIK uses a version of Obelisk which was not originally developed to be used as a web platform. And that's why we have two different flows here. And remember, in the beginning of my presentation, I talked about how we needed to split the secret shares, how we needed to split the keys into secret shares and then encrypt those with the public key of the MPC parties, so that the computation, so that the MPC parties can then do the distributed decryption. Well, we need to store those key shares, and that's where we use Redis. So the encrypted key shares are stored there, but only for a certain amount of time. So we use the expire at functionality of Redis, so that if the Redis data store would be compromised somewhere in the future, sometime in the future, the older keys are removed, are not present anymore. Even though they are encrypted with the public key of the MPC parties, it's better to remove them when they're not needed anymore. An example of this is shown here. And what we can also see here is that alongside the encrypted key share here, we also have an analysis ID. So to make integration better with the different parties, the MPC party should know as little as possible about the user's data. So when the user creates a request for computation, it creates an analysis ID, and then a lot of metadata about that analysis is stored in the metadata store. So then the MPC parties only need the analysis ID to query the actual data. So they don't really need to know the actual data sets where the data is stored. They only need the analysis ID. So it's good for abstraction, and also allows for time series database mapping. So we can store timestamps. So we don't need to enumerate all the entries in the data in the time series database. And in the metadata store, the MPC parties are also registered. Quick example here, you can see that this analysis ID stores the source and result data set. So source data set is where the original data is stored, and result data set is where the machine learning inference results should end up. You can also see different MPC parties involved in this computation. And also, for example, the analysis type, which is then the type of machine learning inference. We also store the MPC parties in the metadata store, like I said. And in this case, we only have a region keyword, but in practice, you could easily add some trust level, some reviews, maybe the cost per computation. But this is useful for the user, so that the user can select which MPC parties they actually trust and which ones they want to work together on for computation on their data. And what we see here, the MPC key, this is the public key of the MPC party that's needed to encrypt the key shares. What we also do in Obelisk, in MOZAIK Obelisk, is we do hardware isolation. So we really try to physically isolate services that shouldn't, that are high risk. And what we also do is, alongside physical isolation of services on different nodes, we also use secure containers. In this case, Kata containers, which uses micro VMs, which are lightweight virtual machines. So they use hardware virtualization and it still works together with Kubernetes. So different services are better isolated, whereas if we just rely on C groups, for example, or simple run C containers, Kata containers has higher overhead but better security. And we also use the Kubernetes principle of anti-affinity or affinity rules, where different services are placed on different nodes depending on different properties. For example, the API runs on a completely separate node than all the other services, because that's considered a very high risk service, because that's the one that's publicly available. And then we also have some network policies to prevent unauthorized network access. So different pods that don't need to communicate with each other are blocked on a network level. And this is also useful, for example, if somehow one of these services gets compromised, that we also prevent network access to different services. So we try to prevent the lateral movement. And then the dashboard, this is just a website we have built for the proof of concept. But in reality, if you want to implement this in a real case, you would probably rebuild the website, because it's not that user-friendly, even though it says it's user-friendly. You can request analysis, you can look at the statuses, and look at the results. And this is built with SvelteKit, not that important, but this is just a front-end framework. And now it's time for a quick demo. So I will switch to the dashboard and quickly show the different options there and how we can request an analysis and then look at the results. So let's. So it should now show the dashboard, if I'm not mistaken, yes. So on this page, the user has to provide some credentials. So the first two values are client ID and client secret are obelisk-specific credentials. Then we have the user's public key, which we don't use at the moment. While we were researching this project, we, instead of using the distributed encryption, we might have thought to use the public key of the user to encrypt the result, but in the end, we didn't do so. So this is just a field that can be omitted. Then the user at the moment needs to store their IoT key that has been used, so that's the key K, that has been used to encrypt the data, because the website needs to split that key into secret shares and encrypt them with the public key of the MPC parties to start a computation. But this is all stored locally. So this is stored locally in the browser. This never leaves the browser in full. And then we have the two data sets. So the IoT data set is where the original data is stored, and the result data set is where the result should be stored. The reason why we split this is to make so we can use access control for the MPC parties. So the MPC parties can only read from the IoT dataset, and they can only write to the result dataset. When we look at the data, this is all the encrypted data currently available for this user in this dataset. And this is data that has been ingested using the IoT device simulator and encrypted, of course. The user can here select different data points they want to compute, and they can also select which MPC parties should do the computation. In this proof of concept, we only have 3, but like I mentioned, this list can be very long with different providers providing their computation resources to this platform, and then the user can select based on cost, trust level, and so on. So let's quickly try to do an analysis of one data point, for example. We want to do this with 3 MPC parties because this is how the proof of concept is implemented. And then the analysis type is the actual type of machine learning inference that needs to happen. For example, in this case, this is heartbeat demo 1, so it will do a heartbeat analysis data. And then the expire date is the date that the key shares will expire. So if the computation, for example, is queued for longer than a day, then the keys will be removed from the key store, and the computation will be cancelled. And now if we prepare the analysis, we can see that an analysis has been created, an analysis ID. And we can see now that here we have an analysis that has been prepared, so it has not been computed yet. And the reason why is that we can also batch computations. So if we now create a separate analysis with a different data point, with the same MPC parties, of course, then we will now see that we have two analyses created. They are both prepared. And the reason why we have batching is to enhance throughput. This is especially useful in the streaming case, which I will come back to later. So now someone can queue a new computation. So in this case, we want a batch size of 2 because we have 2 computations and we have 2 analyses in the batch. So we can create a new batch request with 2 analyses, which each have 1 data point. If I now queue the batch, we can see that the batch has been queued. And if we can look at the overview now, we can see this last one is the one I just created. The computation is already completed. So the MPC parties now each received the 2 encrypted shares, 2 encrypted data points from the user. They received the encrypted key shares of the user. They did the distributed decryption, then they did the machine learning inference, and then they did the distributed encryption, and then they sent the data back to Obelisk. And this all happened in under a second. We can see that if you look at more info, this is just some information that's also stored in the metadata store, which analyses are involved in this batch, for example. And now we can look at the results. So we have 2 created analyses. They are now both completed. So this is the first one I created. And we can look at the results. So we need to decrypt the analysis results because the results of the analysis are also encrypted with the secret key of the user. So we can decrypt them because they are stored in the browser. And here we can see that each MPC party will respond with a result. And we need to make sure that the 3 results match, because if one of the results does not match, that means that one of the MPC parties might have tried to do something weird with the data. They might try to give wrong data back to the user. So we need to make sure that these are all 3 the same. If not, then we know that the computation, that the results cannot be trusted. And what we get back is an array. So the top one is just the raw data, but if we parse it, we get back an array of confidence numbers, indicating a certain confidence that the user has a certain heartbeat anomaly. So it's a classification algorithm. Now in the streaming use case, we can enable streaming also. So we can, for example, enable streaming for a batch size of 4. And what this will do is that now that streaming is enabled, every data point that comes into the system, that's being ingested into the system by this user, will be put in a batch. And once this batch is full, for example, in this case 4, once the batch reaches a size of 4, then that batch will be batched off to the MPC parties for the computation. And this allows for near-native computation results while still being privacy preserving. What we also have with streaming is that streaming is disabled automatically after a certain chosen time. So if the user does not stop streaming here right now, so if they don't revoke consent here with stop streaming, their consent is automatically revoked when they reach the expiry date. So if a user accidentally enabled streaming and forgot to disable streaming because they set an expiry date, streaming will stop eventually. And then we have, for example, here we have a batch that has been created using streaming with a batch size of 2. And then these are the two ingested points that were ingested using streaming. And just as the regular result analysis, we can also look at the results. I will go back to the slides. Yes. I will quickly skip some slides. These were some slides in case the demo wouldn't work, that I could still show something. For streaming, I just talked about this is very useful for anomaly detection. So on the left figure here, the left side, this is the one I just shown with manually queuing a batch. So what happens here is data is being ingested into the system, and then the user manually starts an analysis and manually receives a result. Whereas in streaming mode, the data is being ingested constantly, and the data is being processed constantly. This is an example of when streaming is actually ongoing. Then you can see that there are the different batches that have been filled. In the beginning of my presentation, I talked about that we have some more technical information about this, some more low-level information, and this is written down in papers, but also in deliverables. But the first paper I want to highlight is this one. This is a high-level introduction of MOZAIK when we first started the project. So we brainstormed, and then we had the very first proof of concept of the architecture, and this is written down here. But here we also focus a lot on GDPR and for the privacy, to make sure that everything is privacy compliant. We apply Linden framework here. So this is very interesting if you're more interested into the design of MOZAIK in the original stages. And then if you're more interested in how the key management worked for multiparty computation, so what I talked about with the splitting the keys into shares and then encrypting those, more low-level details are written down in this second paper here. Then we also have a third paper, which is currently in review, so I cannot share this at the moment, unfortunately, but this is a paper we have written completely at the end of the project with everything we've learned, all the low-level details of the whole project with the final architecture. So once this is published, I really recommend you to have a look at it if you are interested in more low-level details about how we implemented certain things. And with that, I would like to thank everyone for being present. If you have any questions after this presentation, feel free to email me. My email address is on screen, or you can also find me on LinkedIn. I'm not sure if the slides will be shared in a PDF, but if they aren't, and you would like a PDF version of the slides, you can also email me. And with that, I would like to ask if there are any questions.
Thank you so much once again for the presentation. I think it was a very nice mix of an overview on how things work, but also technical enough to fully understand what you've been doing, which is quite interesting indeed.
Yeah, it was hard
the Q&A.
Yeah, sorry, it was hard to find the balance between how much low-level detail I can share, because you need a lot of previous knowledge to really understand.
Well, luckily for who's been following us already for a while, we had opportunities to present part of what you said today as well, in terms of, for example, a more technical explanation on multi-party computation. We had an introduction to Obelisk as well. So it's also nice to see all the pieces that now are combining together, that they would give a nice overview, let's say. But yeah, thank you again. I have just a couple of questions for you while we wait if there are more that are coming from the Q&A section. Well, first, maybe something that could be interesting is if you see, let's say, limitations or maybe challenges is the better word in terms, especially since you're dealing with IoT devices. You know, they open up the door to a big range of a huge range of potential challenges. Do you see any that are the most relevant for this case?
Well, for most of the IoT sensors, in this case, we try to prevent all of those security vulnerabilities by using 5G network slicing and making sure that the devices are up to date. But if we just look at the whole platform as a whole, the biggest challenge is the overhead of MPC itself. And also because you're working with encrypted data, so this adds a whole layer of overhead. And if low latency or really low latency, almost real-time anomaly detection is needed, then this is not the best solution.
Yeah, I mean, that's something intrinsic, I'd say, on multi-party computation. We heard often that there's an issue with the overhead. So I guess you could do up to a certain point to mitigate the problem, but not solve it completely, very likely.
Yes. To try to make the overhead as little as possible, the guys at MOZAIK developed a lightweight encryption algorithm so that the encryption and decryption is as fast as possible, but still there is a certain amount of overhead. Really, if you compare it to native, I don't know the numbers on the top of my head, but let me quickly get the paper results here. If you look at just a regular, so one data point, so if you want to process one data point with the exact same machine learning model in MPC or in plain text, we see in plain text it's 6 or 0.6 milliseconds, and in FHE, in MPC, sorry, depending on if you are working in the semi-honest or the malicious setting, it's 0.08 seconds or 0.15 seconds. So it's really a jump of times 10, times 100 sometimes as in overhead.
So that's something to keep in mind indeed.
FHE is an even more ridiculous. It takes 40 seconds for the same data point. So, yeah.
Something to keep in mind, indeed. Okay, maybe another quick question. If someone would like to use MOZAIK or like would be part of it, do you have any preferred way to interact with them, or like what someone should do to be part of it or be using it?
All the code is available open source in the I will maybe open it up again. In the GitHub organization, I will use this here. Here. This is the GitHub organization, MOZAIK-SBO. Everything is open source here. So if you're interested in any of the different components and implementation, feel free to look at the organization. If there is something not clear, you can either create an issue in one of the repos, or you can email me, for example, and then if the question is more related to low-level cryptography, for example, then I will make sure to forward the email to the correct persons in KU Leuven so that they can respond.
Okay, fantastic. I don't see any other questions. So for the moment, once again, thank you for the presentation. I will thank also all our public here that followed live, and anyone else who will probably watch this recording later. I'll just remind that next month we're going to have our monthly webinar. We're going to change completely topics. So the 12th of August, we're going to talk about serverless computing, which is another big topic for OpenCloudification. So Thank you again, everyone, and I'll see you next time.
Thank you.